In this video, we will use the regression that we created during our last video to use the a, b, and c parameters to generate a new function, and then use that function on a slope calculator to determine some new velocity data. And that velocity data will actually be instantaneous velocity. So just a quick recap, we used regression in the last video to obtain our a, b, and c constants, or coefficients of our general form quadratic equation. And all I've done since the last video is I've taken these constants, rounded them to 3 decimal places, and created a function that you can see down here on line 5. So I'm going to take that function, copy it, and move it over into our quadratic slope calculator. You can see I've pasted it in on the top here. Why we do this is it allows us to use the slider to sort of probe the rate of change at any given point in time. We know that if we take a tangent off of a curve of a displacement time graph, which is what this red parabola is, the displacement time graph can give us the velocity. In this case, the tangent and its slope is known as the instantaneous velocity. So what we can do here is use this to create some xy pairs, and then we can use those xy pairs to actually figure out what is our change in velocity over time. So what we're going to do here is use this little manual data entry tool, and we'll start at 0. So I'll just type in 0 here, and what we can see is on the next line down on line 3, that slope m is equal to 0.226. So what I would do is I'd open up a new Desmos tool, and I'd write down 0 and 0.226. This is my time, my x value, and my slope, 0.226, is the m value right here. That would be my y. So we're going to create a series of these data points into a chart, and as we do that, we should get a nice graph that is formed. So I'm going to go ahead and do that. I'm going to open up a new Desmos graph. So I think I can right click on Desmos and open in a new tab. I can then click on Open Graphing Calculator, and we'll get started, and I'll just show you a couple and then I'll sort of fast forward it. So I'm going to come up here and go plus table, and this will give us our data table, and then for time 0, okay, because that is this a value here, we can write down 0.226. So that'll be my y, so 0.226. What I'll then do is I'll come back to my equation, and I think what I'll do is I'll increment by 1/5 of a second, so 0.2 will be my next value of interest. I can see that the slope has gotten steeper, both numerically and visually on the graph. So in my data table, I'll write down 0.2 and 0.4912. So 0.2 and 0.4912. All right, so I'm going to go ahead and fast forward this. I'm going to create probably about 6 data points, and then we'll come back and talk about what this all means. All right, I have my data entered here. I've sort of probed for 1 second of time just to see what is my rate of change. And it's becoming pretty apparent that we do have a linear relationship. So with that in mind, I don't think I have to go too much further past the 1 second mark. You may want to go maybe up to like 1.2, 1.4, just get a couple more data points if you find that your line or linear relationship is not coming out really true. And that'll help with the average regression or linear regression that we're going to do here in a moment. So what that means is that the rate of change here, as I go up this curve, is going up by a known value. We have a nice line here, and that known value is going to be our acceleration, which we can get through a linear regression and finding its slope. We can now go ahead and create our linear regression. We can see that we do have a y-intercept value when x is equal to 0. It's currently set to 0.226. We can see that on our graph as well. So that just means that our cart had some velocity before it crossed that first line that we used as a data point in the original video. So what we're going to do here is come down to line 2, and we're going to start typing our linear regression. So we're going to type in y1, which will help us target this y1 data column. And we're going to set it approximately equal to by using the tilde sign. And then we're going to write in the equation for a line, mx1 plus c. We're using x1 here to make sure it uses this x1 data set, okay, this column of data above. We can see here that the c value does come out to be 0.226, which is nice because it lines up with our data table up here. So when x is equal to 0, what does y equal? That is the definition of your y-intercept. And we can see that the value here of 0.226 and the value up here, 0.226, are indeed the same. So that's kind of nice. It's just a little bit of extra proof to show you that this is all working properly. We can also see that our line passes through all of our data points. We can see that our r squared value from a statistical standpoint is bigger than 0.95, so the fit is pretty good. In this case, 1 is really good. And then we can see that our slope for this line is 1.326. That 1.326, the slope of our velocity time graph, we know from class, is our acceleration. Because we have a linear relationship here for velocity time graph, we must have a uniform acceleration value on our acceleration time graph. So if I take this graph and I use its slope value, I can sort of plug in one more equation here. I'll just set it equal to y equals 1.326. And that green line that pops up would be our acceleration time graph line, because we know that our relationships provide a relationship between displacement to velocity, but also velocity to acceleration. If I go from position to velocity, or displacement to velocity I should say, if we start with a parabola, we know that that results in a rate of change that is uniform, and that is shown as a diagonal line. And if I go from my velocity time graph, which is that diagonal line, and I go to acceleration time, we can take the slope of that velocity times diagonal line, and that would equal the acceleration. And that has a lot to do with how those formulas have been taught to you in Science 10, with acceleration equaling the change in velocity over time, which is very similar to the slope formula, which is slope equals rise over run. So in this case, our change in velocity is our rise, and our change in time is our run. So if I take my change in velocity and divide it by my change in time, I get acceleration, and that is the definition of slope, my change in my velocity over my change in time. So that is why the slope of this line equals acceleration. So I can graph that out, and we can see it is a flat line. It has zero slope itself because it is a constant. It's just y equals 1.326. So we get a flat horizontal line. So that's pretty nice to be able to see that relationship between this quadratic equation here, the parabola that is generated. We can see that the rate of change is ever increasing on the right hand side here. So we're getting a positive value as our slope increases. And then as we take that and graph it, we can get this linear relationship for velocity time, and then we can go one step further and take the velocity times graph's slope, and that is our acceleration time. So this is a very nice tool to help us understand and explore the concepts of displacement, velocity, and acceleration, and hopefully these videos helped you with your lab.